Hauling a freight train weighing thousands of tons from a dead stop is a brutal exercise in physics. Under immense strain, steel wheels naturally want to break traction, spin out, and grind against the rails, wasting massive amounts of kinetic energy. For decades, engineers relied on raw weight and manual operator skill to manage this struggle. Three-phase electric locomotives discard that approach entirely. They solve the physics problem of heavy hauling by replacing analog, mechanical reactions with real-time microprocessor control. We can see this exact engineering directive laid out in the official electrical locomotive manual. Under Section 2.1, Point 1 establishes the baseline for the entire machine. Digital electronics now provide real-time traction control. In practical terms, this means the locomotive's onboard computers calculate the precise amount of grip available on the rails and adjust the power output to the wheels instantaneously. This happens entirely independent of the human pilot pushing the throttle. This digital architecture requires three operational pillars to function: intelligent traction to generate movement, electronic braking to arrest it, and dynamic auxiliaries to keep the systems alive. Of these three, intelligent traction is the most critical. It is the primary method for ensuring that thousands of volts of electrical power actually translate into forward physical movement with failure. A modern three-phase locomotive operates as a predictive digital platform. It manages physical forces by calculating outcomes faster than human reaction times allow. Heavy acceleration causes a phenomenon called load shifting. As the train pulls forward, the sheer physical resistance forces the locomotive's weight to rock backward. This lifts the front wheels slightly, instantly causing them to lose grip and slip on the steel rail. Look at this physics vector diagram of an accelerating bogie. To mitigate the upward rotational force, engineers install a mechanical traction bar system. This physical stabilizer anchors the bogie to the main body of the locomotive, aggressively counteracting the lift. Hardware alone cannot solve load shifting perfectly. The locomotive pairs that mechanical bar with an active software intervention called electrical weight transfer. As the physical weight shifts backward during acceleration, the microprocessors deliberately starve the front bogie of tractive effort. By cutting power to the exact wheels that are lifting, the software prevents them from spinning out. Simultaneously, the system diverts that exact power into the rear bogie. Because the weight shift has driven the rear wheels harder into the track, they have naturally increased physical adhesion, allowing them to absorb the extra electrical thrust. Track conditions inevitably degrade due to rain or track wear. When that happens, the system relies on Point 3 of the manual, the active anti-slip protection protocol, defined by a strict 0.5 mathematical ratio. The software constantly divides the effective tractive effort, the actual grip on the rail, by the requested tractive effort dialed in by the pilot. The moment that ratio drops below 0.5, the computers instantly override the pilot to cut power, proving the wheels are spinning uselessly. Some specialized passenger units, like the WA5 class, integrate an automated wheel flange lubricator directly into this process to manage the physical friction of cornering. Spraying precise amounts of lubricant on the flanges reduces the brutal metal-on-metal wear. This directly extends the operational lifespan of the wheels and noticeably lowers the electrical power required to drag the train through tight curves. Generating forward momentum requires micromanaging physical grip. By balancing mechanical anchors, intelligent weight transfer, and automated slip math, the locomotive prevents wasted grid energy and catastrophic wheel damage. Arresting the momentum of a multi-ton freight train requires the exact same level of digital precision, governed by instantaneous electronic brake systems. Pneumatic air brakes are highly effective, but they present a massive safety paradox. How do you guarantee a moving train will stop if the high-pressure air systems entirely fail? This schematic reveals the spring-loaded parking brake architecture. High-pressure air is pumped into the cylinder, but its purpose is not to apply the brake. Instead, the air pressure is used to physically hold back a massive, highly tensioned steel spring. The system requires active pressure to move. If that pressure drops to zero, through a severed line or total locomotive failure, the air can no longer hold the spring. The coil violently expands and permanently locks the brake pads against the wheels.
Getting the train moving again after the brakes have locked requires rapidly refilling those cylinders with high-pressure air. Point 18 of the manual outlines the quick-release mechanism. To force the heavy springs back into position quickly, the pilot temporarily overcharges the main brake pipe pressure up to 5.4 kilograms per square centimeter. Sustaining that high pressure would damage the internal pneumatics. The onboard computer times the overcharge strictly, then automatically restricts and bleeds the pressure back down to the standard 5 kilograms per square centimeter. To eliminate the complex maze of overlapping copper pipes required for these systems, engineers consolidated the pneumatic routing into a single, highly accessible three-fold pneumatic panel inside the locomotive. The mechanical application of these pneumatics is handled by compact tread brake units. Integrating these modular TBUs drastically lowers the long-term maintenance costs of replacing worn brake shoes in the rail yard. Locomotive safety relies entirely on inverted physics. Engineers build systems that default to a violently clamped, fully stopped state the exact moment human input or internal pressure vanishes. Moving away from the wheels, the internal machine room houses massive cooling fans, pumps, and air compressors. Powering these auxiliary systems can drain vast amounts of electricity from the overhead grid if left unmanaged. This split-screen chart illustrates how the static auxiliary converter solves this. Instead of running internal cooling fans at a constant, maximum speed, the converter scales the power usage dynamically based on what the engine is actually doing. As the traction load drops, for instance when the train is coasting downhill, the converter instantly stretches out the frequency waves applied to the fans. The fans slow down in real time, drastically reducing the locomotive's overall power consumption. Point 21 addresses a major hardware modification to protect these electrical systems, removing the main air compressor from the internal machine room and hanging it underneath the truck of the locomotive. Air compressors require heavy oil lubrication. Suspending the compressor outside the main chassis eliminates oil vapor buildup inside the machine room, removing the primary catalyst for catastrophic electrical fires. The machine room itself is heavily pressurized. Intake air is forced through inertial filters, creating an overpressure environment that physically blocks highly conductive metallic brake dust from entering the room and shorting out the processors. Incoming electrical power presents its own dangers. High-voltage overhead lines are notoriously unstable. Harmonic filter circuits act as a shield, smoothing out sudden, destructive power surges before they can reach the delicate microprocessors. The locomotive secures its hardware, and it enforces strict protocols to secure its human pilot through the Vigilance Control Device, or VCD. The VCD operates on a relentless 60-second loop. The pilot must acknowledge the system by interacting with a control pedal or button at least once every minute. If they lose focus or fall unconscious and miss the 60-second window, the computer seizes control and auto-deploys the emergency brakes. Efficiency in heavy rail requires building a hermetically sealed, fire-resistant environment. The locomotive aggressively monitors the limits of its own hardware and the biological limits of its human operator. A modern three-phase locomotive in motion functions as a rolling data center, constantly processing environmental feedback to maintain thousands of tons of forward momentum safely. The final layer of this digital architecture is the onboard fault diagnostic system, which constantly surveys the health of the entire grid. Instead of maintenance crews spending hours manually testing circuits in the yard, the onboard computers pinpoint exact component failures in real time, logging the exact node that needs replacing before the train even arrives at the depot. Point 5 of the manual highlights the ultimate diagnostic tool, the simulated operation mode. Engineers can boot up the locomotive's complete logic and software suite to run full system tests without raising the pantograph to connect to the deadly 25 kilovolt overhead power lines. Every system we've explored, from the micromanaged traction transferring weight on the rails, to the spring-loaded pneumatics clamping the brakes, to the frequency converters throttling the fans, is interlinked through shared logic circuits. In this architecture, software instructions dictate the behavior of every physical component. The three-phase locomotive's marvel is its evolution from an analog machine requiring physical driving into an autonomous ecosystem that only needs to be supervised.